In the talk, I thank the organizers for giving me a chance to give a talk here. And the reference to this work is this particular paper. You can go through it for many more details of the work. And I thank SCRB and University of Hyderabad Institute of Eminence Directorate for funding. Okay, to begin with, Josephson effect. So what is Josephson effect? So let's say you have two superconductors and there is a difference in the superconducting phases. Phases in the sense the sparing amplitude for the superconductor has a phase also. Let's say that is different for two superconductors, and these two superconductors are joined through either an insulator or a metal. Then a current flows from one superconductor to the other. This is an equilibrium current and it's called Josephson effect. And this dependence of this current on the superconducting phase difference, that is called current phase relationship. And to get an insight into how this Josephson diode effect takes place, let us consider a superconductor normal metal superconductor junction. So if you have a normal metal, in the normal metal Hamiltonian, electrons and holes are good eigenstates of the normal metal Hamiltonian. And so there are two sets of processes. That is one where electron moves left and hole moves right. So this set of process, these two processes, they carry current in the backward direction. And there is another set of processes which is like electron moving to the right and hole moving to the left. These two processes carry current in the forward direction. When there is a superconducting phase bias, one of these processes has a higher probability weight compared to the other. That is why there is a net Josephson current that is carried. Okay, so coming to the Josephson diode effect, so it basically refers to unequal magnitudes of maximum and minimum supercurrents in the current phase relationship. So current phase relationship, generally it is something like I is equal to IC sin phi, but it can be more complicated than that. So when it's IC sin phi, the maximum and minimum are equal in magnitude. But in general, it can be different. And that is what Josephson diode effect is all about. And you need to break time reversal symmetry and inversion symmetry to achieve this Josephson diode effect. And band asymmetry, that can result in Josephson diode effect. That was discussed in this paper. What is band asymmetry? Band asymmetry simply means that at a given energy in the dispersion for a normal metal, let's say the velocity of the forward mover and the backward mover, they are not equal, let us say. So that is what band asymmetric metal means. So in such systems, Josephson diode effect appears. And it's rooted in this magnetochiral anisotropy, which is basically what I told you in systems with spin-orbit coupling and Zeeman field. Okay. So studies have mostly focused on two-dimensional systems with spin-orbit coupling and Zeeman field, where this Josephson diode effect is studied. So we were interested in this thing that in purely 1D, one-dimensional junctions of superconductor, normal metal superconductor junctions, so whether Josephson diode effect shows up or not. That is what we were interested in. And one calculation that we did showed that if the superconductor also has spin-orbit coupling, then Josephson diode effect shows up in these systems. Otherwise, Josephson diode effect doesn't show up. Fine. And there are Josephson junctions involving triplet superconductors with ferromagnetic materials in between. So in these Josephson junctions, anomalous Josephson effect is there. So which is basically that even when there is no phase bias, even when the phase difference is zero, then also the Josephson current flows. So that is anomalous Josephson effect. So the question that we posed was, Josephson diode effect, does it show up in one-dimensional Josephson junctions with superconductors having triplet pairing along with the singlet pairing? And we find that in these mixed singlet-triplet pairing superconductors, both Josephson diode effect and anomalous Josephson effect, both of them show up, which would have been otherwise absent if the superconductor was purely singlet. And so the system that we study is basically mixed pairing superconductors on two sides with a quantum wire in between. And the quantum wire has spin-orbit coupling and Zeeman field, and the directions of this of the spin-orbit field and the Zeeman field, they are parallel to one another. And this is the current phase relationship for three different choices of the triplet pairing amplitude. So 1, 5, and 10. So these are the triplet pairing amplitudes. And you see that the Josephson diode effect coefficient, it is large when the triplet pairing amplitude is large. And so this Josephson diode effect coefficient, it basically quantifies the Josephson diode effect. So the extent to which this happens. So it's basically defined as the difference between the critical currents in the two directions divided by the average of the critical currents. You can see that for this green dotted line, the Josephson diode effect is maximum. That is the maximum and the minimum in the current phase relationship. They are much different in magnitude. Okay, so let us see why this happens when there is a triplet pairing. So let us say there is singlet pairing. So as I said, so it's the electrons and holes in the normal metal which carry the Josephson current. So in the normal metal, when there is singlet pairing, a downspin electron, for example, so it mixes with upspin hole. And a downspin electron moving right, it gets converted into an upspin hole upon reflection, and the phase picked up in one back and forth reflection for states carrying current in the forward direction, that is this. So that is basically the this k minus the other k into the length. So the phase picked up for the processes that carry current in the forward direction and the same thing for the backward direction, they are exactly equal for these two sets of processes. So that's why when there is a singlet pairing, the Josephson diode effect doesn't show up. But when there is triplet pairing, and a downspin electron gets reflected as a downspin hole. And if you see the bands of the downspin electron and downspin hole, you see that for the processes that carry current in the forward direction, the phase picked up is different compared to the phase picked up by the processes that carry current in the backward direction. So this is the root cause of the Josephson diode effect when there is a triplet pairing. Okay, so this is Josephson diode effect coefficient versus the ratio of the triplet pairing to the singlet pairing amplitude for one particular set of parameters. So initially, as the triplet pairing amplitude increases, the Josephson diode effect magnitude increases, reaches a maximum and then decreases. The reason for this decrease is a competing phenomenon, which is that when your superconducting gap increases for the triplet pairing, more and more states within the normal metal, they participate in the transport. And these are at different energies. And the states at different energies, they favor the supercurrent in different directions. They favor Josephson diode effect in different directions. So on the whole, it kind of gets cancelled. So that's why as more and more states start participating in the transport, so the diode effect coefficient, it decreases. So this is a plot of the diode effect coefficient versus theta, where theta is the angle made by the triplet pairing amplitude. So there is the direction of spin. So it's basically up, up, minus, down, down. So the direction of this up in the triplet pairing, and there is also direction of spin orbit field. So the angle made between these two directions, so that is theta. So you see that as a function of theta, this is the dependence. And interestingly, for when the singlet pairing is exactly 0, for theta equal to pi by 2, the Josephson diode effect is absent. That is because the pairing is simply up down plus down up, and by the argument that I gave earlier, upspin mixes with upspin electron mixes with downspin hole, there is no Josephson diode effect. Okay, so this is what I told you, and this is the dependence on the chemical potential in the central normal metal region. And with the chemical potential, it shows Fabry-Perot type oscillations. One can show that it is rooted in Fabry-Perot type oscillations by looking at the periodicity. Okay, so this is the summary, and this is the paper if you want to look at more details. Thank you very much.
Questions? Okay, if there is no question, let's thank to the speaker.